So we can continue. Today we have the most interesting topic. It's about spectral response measurements. So it's a little bit complicated but interesting. So first of all, why do we need to measure the spectral response? So the main reason that we have to distinguish between different types of losses. So if you want to distinguish between optical and recombination losses, it could be not so easy to do it if you have just IVQ. So you have a low short circuit current, it could be due to the recombination losses or due to the optical losses, for example, higher reflectance. And another case, it's the analysis of quantum efficiency spectrum. It could give more information. So if you want to select the losses components, I mean to distinguish between different type of loss and define the origin, if it's interface recombination or bulk recombination. And then once we have get this idea, we can find a way to reduce the losses. So for this we need spectral response measurement. And also, as I described last time, we need quantum efficiency spectrum to calculate the short circuit current of each subcell. So if we want to know the short circuit current of the multi-junction solar cell, any case, and therefore any measurement of multi-junction solar cell, we have to know the quantum efficiency spectrum or spectral response. It's a little bit the same. So first of all, what kind of optical losses we can imagine? So first of, it's just a reflection, it's clear. Then we have some shadowing by the contact grid. We can get some absorption losses in non-photoactive layers. It means, for example, if you have a transparent conductive oxide, for example, for thin film solar cells or for heterojunction solar cells based on silicon and amorphous silicon and crystalline silicon, we need the TCO layer, which normally should be transparent, so we should have no absorption losses, but in some part of spectrum you can get some absorption, so you have to take into mind. And some part of light could cross through the structure without absorption, so it's also some kind of optical losses. Concerning the recombination losses, it's a little bit more complicated. So we can just define that there are some volume loss, volume recombination, the volume defects. So it's some conventional case when you have defects in a wafer, or for example in a silicon wafer, or in some layers, epitaxial layers, or plasma deposited. So always we have some defects. The question, what is the concentration of the defects, because you understand that in epitaxial layers you have a low concentration of defects, and there's some amorphous hydrogenated silicon, you have a huge concentration of defects. But in any case you can get some recombination losses. So it's just a question, what is the concentration, what is the impact of them. And another case, it's a surface recombination. So it's clear that you have defects at the interface, at the surface. You have to understand that any surface of the wafer, of some semiconductor, and the contact, it's a source of the recombination. I mean, any ohmic contact, actually it's like a source of infinity recombination velocity. So hope you realize it. I mean, there are a lot of ways to suppress the surface recombination or interface recombination. It depends. I mean, if you have some interface between two semiconductor, you can get a lot of recombination losses as interface, and if you have just some homojunction and with the ohmic contact, you would get a lot of recombination as the ohmic contact, and there are a lot of things to suppress them. But here, just to say that in principle, you can maybe not really select, but have some ideas that it's rather some problem related to the top surface or bottom surface. So in general case, it's so clear that if you have some drop of the spectral response at the short wavelength part, it means that the problem comes from the top part of the junction. Why? Because actually, if you remember the dependence of the absorption coefficient on wavelength or energy, so I mean, you should realize that for shorter wavelength you have a higher absorption, and it means absorption coefficient, and it means that the most part of the photons absorbed near to the surface. For the high wavelength you have a lower absorption coefficient, so it means that they absorbed in the volume, and if you have some drop of quantum efficiency at the high wavelength, it means that you have some problem either in the volume or at the bottom interface. So then it's a question how to analyze the exact origin of this losses, but general cases you can at least select the area of the recombination losses. And now what is the quantum efficiency? I mean, the term of the quantum efficiency, actually there is a quite strict definition. We can speak about external quantum efficiency and internal quantum efficiency. So the most interesting parameter is the external quantum efficiency, because actually it gives you information about the quality of your solar cell. But if you want to analyze the things like recombination losses and to distinguish between the origin of the losses, you have to know the internal quantum efficiency. So external quantum efficiency, actually it's quite easy. So it represents the ratio of electron hole pairs which are selected by the some p-n junction or any field, and come to the external circuit. It means that they are not recombined in the volume at the contact. Anyway, they have reached the external circuit. So actually it means that they have some impact to the photocurrent. So you just measure the photocurrent, and so divide it by the number of the total photons. So actually it's the ratio of electron hole pairs which are selected and comes to the external circuit to the total number of the incident photons. And so in the sense that in a very I would say nice case, you would get 1 or 100%. So actually it is not unrealistic. I would say in at the several wavelengths you can get up to 100% quantum efficiency. But don't miss it with the efficiency of solar cell, because it's a quite different thing. So you can get the quantum efficiency at some specific wavelength quite near to 100%, and then get 1% of efficiency of solar cell. It would be not so possible to get 1% efficiency at the whole range of the wavelength and get a high efficiency of the solar cell. But I would say that don't be afraid if you calculate the quantum efficiency of 18, 19 or even 95% for some at some wavelength. For solar cells, it's not so unrealistic. Moreover, there is theoretically there is some possibility to get the higher than 100% of quantum efficiency if you have some multiplication. So, for example, due to the 1 photons, you can get not only one but few electron hole pairs. So it could be predicted for several cases, but in practice for solar cells, I mean, if you work at short circuit current, if you have a look to the short circuit current, not if you do not apply a huge reverse bias, normally it's the quantum efficiency in practice is limited by 100%, because there could be some theoretically some mechanism to get more the 1 electron hole pairs by photons, but in average, I mean, because you have always some recognition losses and etc. So it's always a question to check if it's above 100%. So, concerning the internal quantum efficiency, I'm sorry, here it should be internal. It is a little bit more insight into the structure. You have to think about the electron hole pairs the same, which are separated and come through the external circuit, but divided to the number of the absorbed photons. So it means that in this case you do not take into account some reflections, shadowing, and if there is no absorption. So just take into account only the photons which are absorbed in the active layers. For some case, if you have no losses due to transparency, if your solar cell is not transparent, so we can just divide it, use this formula, take into account the shadowing or by the contact grid, and take into account the reflection. So you can simply calculate internal quantum efficiency from external and by measuring of the reflection. So the same, if you want to be very accurate, so you can also take into account the transparency. You can divide it 1 minus transmittance, and then you can get the value of the internal quantum efficiency. But the main idea that external quantum efficiency, it's like a IV cube. It's some parameters which represent the quality of your solar cell. So because for normal solar cell you have to decrease the reflection losses, the shadowing, decrease anything, and so it's like some device characteristics. If you want to analyze what really happened inside the solar cell, inside the structure, you need the internal quantum efficiency. So it's some words about why do we need it. And then it seems to be quite easy to measure the quantum efficiency, because so you just need to measure the photocurrent at some wavelength and just know the number of photons. So as usual, it starts from, seems to be easy to measure, and actually it's not so difficult, but again not in case of a multi-junction solar cell. So in case of a multi-junction solar cell, it's usually it's not so easy. The main problem is that, so if you have two junctions which are connected in series, and then we want to measure the response from one junction, for example from the top junction. So you use some monochromatic light, for example a blue light. There is some absorption and generation of the current, but for the bottom the light is absorbed in the top junction, and there is no light in bottom junction. So it means that the bottom junction generates zero current. So you know, we are in series, we are limited by the lowest current, and it means that there is no current here. So in ideal case, you would measure zero current. Then if you want to measure the bottom junction, you can try to use the light of the long wavelength, and it gives some current here, and almost zero current at the top junction. So again, have a problem. If you want to use some light bulb, so another problem. So it's even technically it's not so easy to measure. Actually, for non-ideal case, I would say if you have some leakage, you can get some measurements when you try to measure one junction, but you have a response from the another one. So, and you have something that really doesn't correspond to separate junction. And because actually there is another problem, that if you want to get a spectral response, you want to get a spectral response of the separate junction. So, for example, from top and from bottom. So, one of the way to do it, you can just prepare some special structure with, for example, here 3 terminals. So you can imagine it with some special structure with intermediate contact, normally using some lithography, etching, etc. It's really not so easy. Another solution to prepare some special structures with when these layers corresponds to the thickness to modulate the absorption, but there is no p-n junction, only of one type. For example, if we have p-in junction have here, so in this case we have to deposit p type amorphous silicon, but actually you can get some series resistance, some for heterostructures with the heterojunctions. You can get some additional potential barriers. So it's not the good way. And actually, it's the main task is to measure the real solar cell, I mean multi-junction solar cell. There is a way to perform the measurements for this kind of solar cell using the bias light. So actually the idea is quite simple. If you have the bias light in a narrow spectral band, so you can just like switch on one of the junctions to pass the current. Actually the idea is like this. If you want to measure, for example, here the bottom junction, you can use bias light. So we can use, for example, let's call it blue light. So I mean it's a light of the low wavelength with a higher intensity compared to the monochromatic light. And in this case, you generate the current for example, here the top junction. And then using monochromatic light, you can generate another current in the bottom junction. So it leads to the case when the total junction of a double junction solar cell is limited by the lowest current. So it is limited by the current generated by monochromatic light. While you have a current here, so there is no problem with the current limitation. So you can have a look to this IV cube. So this is the IV cube of the top junction. You see it is illuminated, and so it has a high current. So you have to understand that it's like some. If we want to analyze the IV cube of multi-junction solar cell, so we can try to analyze it, the separate IV cube of each junction, but it's some abstract things because it's not real IV cube. It's IV cube of this junction, which would be in case of separate junction. So, but in any case, it gives you idea that you have a higher current here. For the bottom junction, you have a lower current. So, the total current, the total IV cube is here. So, we are limited by this bottom junction. And actually, it's a way to measure the spectrum of the quantum efficiency of this bottom junction separately. I mean, your top junction is illuminated, it has a lot of current, and it's out of the game, and the only response of bottom junction is recorded. So the same thing you can imagine about the bias light for the bottom junction, and using with the same idea. So you illuminate the bottom junction with the light which pass through top junction without absorption. It's absorbed in the bottom junction and generate the current, enough current, and then you use the monochromatic light. And in this case, of course, we have to switch off this blue light. It's clear. So we have to use for double junction. We have to use only one source of bias light and one monochromatic light. So, for example, here, if we consider double junction solar cell based on amorphous hydrogenated silicon and microcrystalline silicon, we have a look to the spectral response, and from this spectral response, we can choose the range of the bias light. So, to measure the bottom junction, we have to use the bias light in this range, where top junction is enough sensitive, while bottom junction is not sensitive at all. And in opposite, to measure the top junction, you have to use the bias light in this range, where top junction is sensitive and top junction is not sensitive at all. So it's the main idea to select the different response of the different junction. Again, if you want to measure triple junction solar cells, you have to use two sources of bias light and one monochromatic light. For example, here you can choose to measure the top junction. You have to use two lights to eliminate the middle junction and the bottom junction, and see to measure the middle junction you use two different lights, so it's etc. So actually seems to be very easy. I mean, so maybe not so easy, but the idea is quite simple. The main problem is that here you already know the spectral response, but actually you want to measure the spectral response, so you don't know exactly. So, but in this case you have, so it depends on the task, because maybe it's already well-known structures, or maybe well-known material, or maybe you, in any case, you have some ideas how to eliminate this junction, because normally you have some ideas about absorption spectra. I would say it's not maybe the problem comes from the case when you have some region where the both junction are sensitive. Actually, so it means if you have the band gap which is quite near, or if you have a thickness quite low, so it's really, it would be a real problem to select. So, but normally for I would say for normal multi-junction solar cells, in any case you have to distinguish the area. You have to select them, because otherwise there is no reason to use several junctions with the same spectral response. Sometimes you maybe have to use really narrow spectral range, for example some laser light, if you want to really distinguish between the elimination of the difference, so the different junction. But normally for source of the light it's LED. It's I would say for the most cases it's narrow enough, but in our practice we're obliged to use laser, because it was quite specific solar cell with very thin top junction with a band gap which was quite near to the middle junction. It was like 2 eV and 1.9 eV, so it was really not so easy to select, to distinguish between, but have done. So I mean, if you use some laser light or something like this, you can manage. But actually the problem of the bias light, to choose of the bias light, it's not the main problem, because as I told you, normally you have some ideas about material, about this sensitivity, and you can get some iteration. You can try to measure to get some approximate spectrum, and then for precise measurement you can to do it again. But there is another problem which could be a little bit more stronger, which comes from let's say, non-ideal solar cells. So the problem that if you want to measure, so using this approach of the bias light, you use some high intensity of the light for the bias light, then the most of the quantum efficiency measurements is performed at the short circuit current condition. So it means that the voltage, the external voltage, is equal to 0, voltage of your solar cell. So you measure short circuit current, so you just measure the current at the external circuit. And then have a look, you have a low intensity of a monochromatic light. You need to use low intensity of monochromatic light because you have to provide the condition of the current limitation. And you have a high intensity of the bias light, and you understand that you have a lot of, it's like you have a lot of current, but there is the current is limited. It means that actually, as I told you, you have a IV cube like this for this top junction, but once the current is limited, you are at this point. So actually it means that the eliminated subcell, it generates the positive voltage. It's like you have because if you have a lot of light, you see, and there is almost no current, you see it generates a VOC. So you are rather in the VOC conditions than in a short circuit current condition. So actually for ideal, I mean for good solar cells, if there is no leakage, so if you have a reverse IV cube which is flat, it gives no problem. So you can measure because you don't care about what happened with this unmeasured junction. But in case of a leakage, there could be some problem, because actually what does it mean? If you have a higher voltage, some positive voltage here, the total voltage is 0. It means that you have a negative voltage at the measured current, at the measured junction. So you are here actually, and if again, if there is no leakage, if reverse IV cube is flat, so we are in the safe. But if there is some leakage, it's maybe not like this, but some dependence, some increase of the reverse current, you would get some problem. I mean, this leakage would give you incorrect measurements. You have some current, and actually it means that you would be sensitive to this unmeasured junction. So you would get some signal here, and in the area where for example, you have no. Normally you should have no current here, but due to this high reverse voltage, you get some current from at this wavelength. So it means when you will register, you will have some response as a wavelength, which has nothing to do with the real response, real quantum efficiency of the solar cell. So first of all, you have to analyze if it could be a case or no, because I mean, if you measure the short circuit, the IV cube, and if you perform some different measurement using the light, and you should have some ideas about the spectral response of each junction in any case. And if you see that there is a problem, this problem occurs, there is a way to avoid it, is to apply some compensative voltage. So if here you apply some positive voltage, you mean in ideal case you would apply the same voltage as for this unmeasured eliminated junction, and in this case here the voltage would be equal to 0, and this, so you are at the desired short circuit current point. So it's just some main idea to apply some compensative voltage, but in practice it's not so easy to do, because actually you have a lot of parameters to vary. You have a light intensity, you have a bias voltage, and then you have a monochromatic light. So you have to check if there is a real nice condition for the measurement. So it's really some iterative process. I mean, it's easy to say how to do it than to really measure it, because you have to find this condition. To vary the intensity of the bias light, the real voltage, because you can get a lot of different the influence of different parameters. So it's not so easy, but there is some general recommendation. So first of all, you have to be sure that the bias light doesn't generate the light and doesn't generate the current in the measured cell, subcell junction. Then I will try to apply the voltage, the positive voltage, which gives the minimum current. So the main idea is, if you, for example, here with this you apply some bias light to generate some positive voltage, you have a negative voltage as a test junction. So the idea is that you, by applying this compensative positive voltage, you shift here versus zero current. So, but if there is no monochromatic light, you have to go to this zero current, and then try to use the monochromatic light intensity, which is significantly lower compared to this bias light. So, but some just generate, because some general idea, I would say in practice you have to get some experiments. It's better to start with good solar cells to feel if you really can select the different junctions, and then you can feel if you have some problems. I mean with the junctions which has some leakage.